How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And I should say, how do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today is the subject of inertia. And I must make the matter, the idea clear, as follows. Here we have a block of wood at rest on the tabletop. And I ask, what does that block want to do? Answer, the block wishes to remain at rest. Supposing now I have double as much block, and I try in turn to put that system in motion. What do I discover? It also wishes to remain at rest. Moreover, it wishes to remain at rest twice as much, and therefore we say its inertia is twice as great. And so you discover at once that I have used the term inertia and referred to the idea of mass as synonymous. So mass and inertia are synonymous. And this is all tied up beautifully in Newton's first law, which says what? If a body is at rest, it wishes to remain at rest. And if it is moving uniformly in a straight line, that's what it wants to do. In English, simply, whatever a body is doing, that's what it wants to do. Let's look at Newton's Latin for it. Newton put it in Latin. Axiomata siva legis motus. Axioms, even laws of motion. Corpus omne perseverare in statu suo quiescendi, and so on. And in English, a little more within our competence. Every body continues in its state of rest or of uniform motion in a straight line, unless there are some forces to divert it. Consider now the following. Here you come on April Fool's Day, let us say, on a package, on two packages resting on the ground. Here is one and here is another. And you deliver, you impose a force on the one. I will, instead of with my foot, with my hand, and it experienced such a motion. The force produced a motion in the body of so much inertia. Now I try it with this one. Hardly as much motion. Why? This one is filled with rags, and this one with two bricks, and this one has the greater inertia. So, the measure of the mass of a body is its inertia. Consider now the two aspects of Newton's first law. A body at rest wishes to remain so. Here I have a heavy block of wood, a hole in it, and I put a dowel rod in the hole. The dowel rod constitutes the handle. How can I put that handle into the block? As follows. As follows. Notice what happens. I hit the handle. The block remains at rest, whereupon the handle moves into the block. That's the first law. The body of large inertia wishes to remain at rest. Let me pursue this in another way to demonstrate the second part of Newton's law. What did the second part say? If the body is in uniform motion in a straight line, that's what it wants to do. I start again. Now I come down on a firm block. The motion of the handle is arrested. The handle and the block were moving. And what does the block want to do? Keep moving. Whereupon it lodges itself more firmly on the handle. Thus do we demonstrate Newton's first law in two parts. Let me do this another way. Very pretty. Very pretty. I have a support and a weight W supported by a string and another string with a loop in it here, which I shall show you. Let me call this string A and this string B. I propose to do as follows. I'm going to pull on string B, the lower string. And I can break either string B or string A by invoking Newton's first law. If I pull suddenly on string B, W wishes to remain at rest, and B will break. On the other hand, if I pull gently on B, A supports W, already there, plus the force I impose. And I shall show you that exactly with this demonstration. Here is a string. Here is a hook. Here is a weight. and the upper string is supporting the load. Here is the lower string, and I am putting a little rod inside here so that my hand is not underneath should the weight fall. I am going to break the lower string. Watch it now, the lower one. There it is, I broke it. Now I am going to change the string. I'm going to change the string. And now I am going to break the upper string by pulling slowly on the lower one. Watch it now. Watch. We hope that breaks. Now, supposing it does not. One is led to say the experiment has failed. And I say, no, the experiment doesn't fail. I have failed to meet the requirements of nature. Watch. I'm going to break the upper string. There it is. And so we can be applauded for success. Consider another demonstration of the same. Here is an enormous weight, 16 pounds. Here is a string attached to it. If I pull on that string in a gentle way, I'll do it by hand, in a gentle way, the string can support the load. Now let me try to accelerate it. What does Newton's first law say? Body wants to remain at rest. It has enormous inertia. Watch it. Do you see? The string has broken. I shall have more to say about this when I talk about Newton's second law. The second law. Consider now another dramatic demonstration. An application of Newton's first law, because we must not escape the fact that these laws of physics, of nature, of science, have vast applications in plebeian things. A brick, a trowel. Cannot the craftsman, the bricklayer, utilize Newton's first law in this way? Notice if he hit his hand with the trowel, he'd hurt it. But he can hit the brick with absolute abandon and feel nothing. Inertia of the brick. Here is another classic, which I like to do because it is so dramatic. A sheet of paper, about 20 inches by 30. 20 inches by 30. 600 square inches. The load on each square inch is roughly 15 pounds. Atmospheric pressure at sea level. Therefore, about 9,000 pounds of air on that paper. That's enormous inertia. Proof. Here is a board, 1/4 inch thick. I put the board under here, and now I am going to try to put that enormous mass of air into motion by a sudden impulsive blow on this end of the stick. The impulsive view that people have is, oh, the whole thing will catapult. No, it will not, because that mass of air is at rest, and Newton said it wishes to remain so. Watch it. It did not move. It did not move. Fantastic. Now, remember, ladies and gentlemen and boys and girls, when I refer to this block being at rest, and then I say, what does it want to do? And the answer is it wants to remain at rest. I would not have you dispose of this as trivia, because it took the genius of an Isaac Newton to establish it. Nothing trivial about it. Consider another dramatic demonstration. Oh, this one is a beaut. Here is a vessel of water, and it has quite some inertia, and I put it on this paper, and I move it slowly, slowly. Remember, this has large inertia. It wants to remain at rest, and I am not trying to accelerate it too rapidly, and thereby friction forces hold it onto the paper. And so I pull more and more and more and more. We're in a little trouble because friction isn't right for me. But anyone in his right mind must testify to the prospect, if I continue in the manner I have been doing, the whole thing will fall down. But if I invoke the laws of Newton, the first law, which says it wants to remain at rest and will refuse to be moved by short-lived impulsive forces, watch it. Are you not surprised that it stayed there? Consider another, more application. Here is a vehicle, and here is a body standing upright in the vehicle. And now I want to show you that if I move the vehicle, The body is at rest with respect to it, and what does it want to do? It wants to stay there. Watch it. And so it did. And that's why when you accelerate a car rapidly from a standstill, your head is jerked back because of the large inertia of the head. On the other hand, if the car is moving uniformly, if I now suddenly arrest its motion, what will the block do? Well, the block was going straight, and that's what it wants to do. Oh, notice I accelerated too fast the first way. There it is, and the block tipped forward. A quick one for your inquiry. Here I have two vessels, and remember the subject is inertia. They each contain 1 pint. And let us say that one is filled with cream and the other with milk. So I have a pint of milk and a pint of cream. Quickly, quickly, which has the greater inertia? That's equivalent to asking which has the greater mass. That's equivalent to asking which has the greater weight. And some are led to say, oh, the cream, of course, because it's thick and sluggish and viscous. Oh, no, mistake. The milk has the greater inertia for reasons, of course, you see clearly yourself. The pint of milk weighs more than the pint of cream. Another demonstration of the inertia again. Here is a stack of coins. They happen to be Australian pennies. Why? Because they have larger inertia than US pennies. And now what can I do? With a thin blade, I can deliver a sharp, impulsive blow to the lowermost one. And what do I hope to see? I hope to see the whole stack remain unmoved. Why? Because it's at rest and wants to stay. There it is. There it is. There it is. And I just love that demonstration. Why? Because it is a classic revealing the beauty and strength and simplicity, in a sense, of Newton's first law. I want to show one more. Remember what the second part of the law said. I would urge you never to forget that the first law has 2 parts, which are rarely ever properly separated. I said a body moving in a straight line wishes to continue so. Here is a ball swinging in a vertical plane, in a vertical circle. I would remind you that at the instant in question when the ball is right there on the end of the string, its motion is tangent to the path at that place, and if I should cut the string or let go of it, the ball would not go radially outward, but would go instantaneously in a direction tangent. So, this introduces here in a passing way the idea of centrifugal force, which is a nasty thing to handle, and often much is said that is wrong. But if I let go of the string at the top, where will the ball go? Tangent. Watch it. There it is, tangent. Now, it is proper, before we conclude a program on Isaac Newton, to show you one of many photographs of Newton. A very important place this man occupies in the history of humankind. And I would hope that when you go to London sometime, you will most certainly go to Westminster Abbey and see where he is buried. And what does it say on that beautiful epitaph? Among other things, let men rejoice that so great a one has existed. So we are coming shortly to the end of the program. One final enchanting thing, an array of cups. If I put this heavy block on them gently, I can drive this spike into that block without the cups feeling anything. Why? Why? Because the block has enormous inertia. If, on the other hand, I drop it, it's going and it wants to keep going. There it is. And thus I conclude, ladies and gentlemen, a program on inertia. And I thank you for your attention.